Imagine the first minute after an earthquake, flood, or fire. Before humans can safely enter, swarms of drones, robots, satellites, and AI agents are already mapping damage, finding survivors, and coordinating response. That is our next venture. So far, we've built a stack. Autonomous agents that think and coordinate, human interfaces that guide complex systems, and bio-AI infrastructures that protect life. Project 16 turns that stack outward into robots acting together when disasters overwhelm human response. When crisis hits, the hardest problem is not only danger, it is delay. Roads fail, communications disappear, and responders lack a clear picture. Autonomous swarms matter because they can enter those critical hours early, mapping, searching, relaying signals, and delivering aid when minutes decide survival. Project 16 is not a single robot. It is a coordinated disaster response network. Drones, ground vehicles, satellites, and AI agents each handle a different part of the mission: mapping hazards, searching for survivors, delivering critical supplies, restoring communication, and guiding responders. The key idea is shared intelligence. Each unit collects local information, while the network turns it into one live operational picture. Think of a disaster swarm as an operating stack, not just a fleet of robots. The robotic layer gives the system bodies: drones, ground units, boats, climbers, and delivery bots. The sensing layer gives it awareness through cameras, thermal imaging, LiDAR, radar, acoustic signals, air quality sensors, and satellites. The intelligence layer turns that data into decisions, identifying people, coordinating swarms, planning missions, and predicting hazards. The infrastructure layer keeps everything alive with mesh communications, edge servers, charging, and logistics hubs. Resilience comes from integration. If one layer weakens, the others help the mission continue. Disaster scenes are visually messy, so AI needs more than a normal camera. Visual models can spot collapsed buildings, blocked roads, vehicles, crowds, fire, and debris. Thermal sensing adds what the eye cannot see: heat signatures through darkness, smoke, or partial cover. Satellite and aerial imagery provide the wider context, while drones inspect details up close. LiDAR, radar, audio, and environmental sensors add structure, motion, sound, and conditions. The intelligence comes from fusion, combining signals, scoring confidence, and turning uncertainty into safer routes and faster rescue decisions. The key shift in swarm coordination is that intelligence moves from the individual robot to the collective system. One robot may see a blocked road, another may detect heat, a third may still have a communication link. Coordination AI turns those partial observations into shared decisions. It assigns the right robot to the right job, reroutes teams when conditions change, and lets specialized units support each other. In disaster response, the swarm is not just covering more ground, it is continuously reorganizing around the mission, using every robot as part of one adaptive network. In a disaster zone, the network cannot depend on a working tower or a distant cloud. Each robot needs enough intelligence at the edge to recognize hazards, map damage, and flag possible survivors immediately. Drones, ground robots, portable relays, and command vehicles then form a temporary mesh, passing messages through whatever links are still available. The system also ranks traffic. Distress signals and hazard updates move first, while routine data can wait. If a robot drops out or a relay fails, the mesh reroutes and keeps the rescue operation moving. Now think of the command layer as air traffic control for disaster response. The swarm may see thousands of details, but responders need clear answers: where it is safe, where people are likely trapped, and what should happen next. Spatial interfaces turn robot data into shared situational awareness, including 3D maps, hazard boundaries, survivor markers, robot routes, and supply drop options. AI co-pilots can summarize changes and recommend priorities, but they must also explain their reasoning. That matters because humans keep authority. The system guides routes, warnings, and escalation, while trained responders make the final life-critical decisions. Once the swarm understands where help is needed, logistics becomes a decision loop. A request is detected, then scored by urgency, vulnerability, distance, and access. The system chooses the right payload, maybe medicine by drone, or heavier food, water, and batteries by ground robot. Routes are planned around debris, weather, and unsafe zones, with relay hubs providing charging and resupply. Delivery is confirmed through sensors or responder feedback, then inventory updates. The goal is simple: move scarce aid to the highest need people before conventional roads are usable. Pulling those pieces together, the mission system works as a closed loop, not a one-way pipeline. Satellites, drones, ground robots, and water platforms continuously sense the environment. Edge AI turns that raw stream into meaning. Survivors, hazards, blocked roads, damaged structures, and safe access routes. Swarm coordination decides which robot should do what, then shifts assignments as conditions change. Robots act, report results, and update the live operational map. Human commanders stay in control throughout, using that map to guide teams, approve actions, redirect assets, or override the swarm when judgment matters most. The same swarm platform can look very different depending on the crisis. After an earthquake, ground robots and drones search voids, map unstable rubble, and guide rescue teams. In floods, aerial scouts and floating payloads help find stranded people and support evacuations. During wildfires, heat sensors track fire fronts and protect responder routes. In conflict or humanitarian zones, swarms may map safe corridors, deliver aid, and restore communications while reducing risk to people. A disaster swarm earns permission to operate by reducing risk, not just moving faster. Safety starts with hard boundaries: geofencing, collision avoidance, fail-safe landing, human override, and abort controls. Trust comes from evidence. Every recommendation, sensor reading, and handoff should leave an auditable trail. Privacy is equally operational. Survivor images, biometrics, medical details, and conflict zone data must be handled with dignity and strict access controls. Finally, the swarm has to plug into the real response ecosystem: dispatch, hospitals, satellites, radios, and humanitarian coordination systems. Autonomy should make command clearer, not add chaos. Picture an earthquake in 2050. Before the first convoy reaches the area, autonomous drones and ground robots are already building a live damage map, scanning for survivors, reopening communications, and delivering small critical supplies. That changes the first hour from waiting and uncertainty into coordinated action. Humans still make the hard decisions, but they arrive with better information, safer routes, and clearer priorities. The biggest impact is not speed alone. It is safer, smarter response when minutes matter most. The big takeaway is that disaster swarms are not just drones in the air. They are coordinated physical intelligence, sensing danger, interpreting conditions, allocating work, acting in the field, and guiding people. That same loop now becomes a reusable pattern for regenerative agriculture, ecological protection, space construction, and urban mobility, where swarms help systems recover, adapt, and thrive.